we are about to start the next session. The first speaker is Mohsen Ghaffari from MIT, who will introduce to us all the important models that you want to know. So distributed, massively parallel, and also local computation.
Thank you, So the organizers asked me to kind of give an introduction to these models and maybe say a little bit about why these things are connected to each other, in what ways the techniques show up from one of these models to the other and help in solving the problem. And it will be a mostly non-technical tour through the models and this connection. And the main concept that shows up in these computations is the locality of computation, which is not so well understood from classical studies of computation. So my hope is that I explain that concept. I'm going to start with the first about 20 minutes of the talk on distributed algorithms. So this is a very classic area, has been studied for now roughly 60 years or so. The origins of it goes back to computer networks in the sense of ARPANET and so on from the 60s, where they were trying to design these, let's say, kind of routing protocols, for instance, where each of the computers on the network should figure out where to send the packet so that it gets to the destination, how to do congestion control and all sorts of things. So that's where the origins comes from. And the basic level of abstraction when we are talking about these models or these settings is message passing as the base of the operations of the system, right? So, there was a lot of studies in these settings, but Nathilineal, when he wanted to prove a lower bound, he actually crystallized a clean model for it, which is kind of a minimal modeling. I'm going to talk about this model. So the assumption is that there's this undirected graph, and this is an abstraction of the network of computers that we have. And I'm going to usually use n as the number of nodes of this graph. And there's going to be a computer on each node of this graph. Okay, so think about these as computers on the internet, for instance. Right? They have identifiers, maybe the IP address or so. Perhaps we can think about it as coming from a small range, from a range of 1 to poly n. Not so important. What's the range? Okay. And the base of the operation in this setting is message passing. Let's clean up the model and think about synchronous message passing, which means we're going to have round 1, round 2, round 3, etc. in the computation. Right? So there's a clear notion of a round. In each of these rounds, each of the computers gets to send a message to each of its neighbors. Okay? So in one round, each computer can send a message to each of its neighbors. Okay? So that's the most basic thing to know about the model. Generally, when I'm talking about the computation in this setting, usually we are talking about graph problems. And the assumption is that at the beginning of the computation, these computers do not know the topology of the entire graph. Okay, so like I'm a computer, I connect to the internet, I don't know what's the topology of the entire graph, right? And in the end of the process, each of the computers should know its own part of the solution. For instance, if I'm talking about coloring of this graph, each of the vertices in this graph should know what's the color of my own node. They don't need to know the color of the entire kind of graph, the coloring of the entire graph, just their own part of the output. And the primary measure of interest has been the number of rounds. How many of these rounds does it take until all the nodes of the graph have finished their computation? Any questions up to this point?
Typically pass the same message to all of your neighbors?
Great. So there are a number of kind of subtleties or nuances to the model. At the moment, I'm not bounding the size of the message. So you might as well imagine that you send the same message to all your neighbors, right? They can read their own part. Let me talk a bit more about these nuances. Mostly for the talk, we're going to ignore all of these aspects. There's one question of, are these messages small or can they be large? Can they be unbounded? For today, we're going to talk about unbounded message sizes. Usually when we are designing algorithms for this setting and we want a nice algorithm, we want these messages to be small, for instance, log n bits. Okay, so that's one thing. The second thing is that, what about the computation in this setting, right? What can one of the computers do? given the data that it has. For today, you can think about unbounded computation. Given the data that you have, you can do whatever computation that is doable on it. Usually, when we want actual algorithms, we want nice computations, let's say near linear time in total in the size of the entire graph. Okay. Actually, the examples of the algorithms that we will see are nice in both of these regards. There's a third aspect, okay, I don't know the entire topology, but can I make some assumption about, do I know n, or do I know n up to a polynomial? Okay, sure. Let's make that assumption. Usually, one can get rid of these, not always, but usually one can get rid of these. Let's make that assumption and simplify it. Maximum degree is another parameter that sometimes helps to know. Let's say up to the constant factor. Now, here's a very simple observation about this model, which is kind of the underlying reason why this model ends up having connections to many other models of computation.
Question. Yeah, so what kind of guarantees do you want at the end? Do you want like priority with priority 1 that everybody has a solution?
Cool. So if I'm talking about randomized algorithms, we usually want to talk about probability 1 minus 1 over poly of n. And being the size of the network. And it's simple to see that for the time complexities that we kind of really target in this setting, like polylogarithmic and so on, probability constant, let's say 2/3, and probability 1 minus 1 over poly log n don't really make that much of a difference. As a matter of fact, your graph might have been a large number of disconnected components. If each of them has only success 2/3, somebody will actually kind of take a long time, right? So you get the right notion is 1 minus 1 over poly of n, and that's what I'm going to be sticking to. So here's that simple observation about this setting, especially when message sizes are unbounded, computation is unbounded, and so on. In one round of computation in this setting, what does a node get to know about this graph? It only gets to know who are its neighbors, right? That's all that I can learn from this graph, right? And without lots of generality, if you're allowed to use large messages and large computation, I can also think about, I receive the entire one-hop topology of the graph, right? More generally, in T rounds, I can think about, I get to know the T-hop neighborhood in the graph, okay? Like each node of the graph gets to know its own T-hop neighborhood in the graph, right? So as a matter of fact, any algorithm that you design for this setting is essentially a mapping from any possible T-hop topology to the output, right? That's what an algorithm in this setting is, right? And okay, so the topology might be kind of decorated with, let's say, the identifiers of the vertices, right? It's not just the kind of the graph itself, but also the identifiers. And if you're talking about randomized algorithms, there's also the randomness of each of the computers. So that's another aspect that shows up in the model. And this locality is a kind of a reason that this model has ended up being connected to things that, at least on the surface, they're not clearly about this computation model. A number of notions of algorithms for large-scale computation. I'm going to be talking about two of them, massively parallel algorithms and these local computation algorithms and sublinear computation. It shows up with a lot of connections to dynamic algorithms, to graph limits, descriptive combinatorics. There are amazing results in descriptive combinatorics, that were or there are parallel results in descriptive combinatorics and in the study of this locality that were found almost simultaneously and completely independently, and by now we understand that they're actually implying each other. Okay, so a number of areas that, at least on the surface, don't seem to have too much to do with this setting end up having close connections to it. I want to make sure that everybody has a good feeling for the model before diving into more recent things. So let's talk about a simple problem. Okay? So let's say I want to color the graph, color the vertices of the graph, with the number of colors being maximum degree plus 1. Okay? So this is the setting. Each of the vertices should pick a color from numbers 1, 2, 3 up to delta plus 1. Okay? As a node on this network, how would you approach this problem? There's a very, very natural idea on what color should you choose, right? For those of you who haven't seen it, any suggestions? How would you pick a color in this setting? Or at least, how would you attempt to pick a color in this setting? Say it again.
Maybe everybody has seen it.
Perhaps everybody has seen it. That's the problem, right? So you pick a random color. Okay, so that's the most basic attempt at this problem. Right, so let's say these are the colors that they picked at random. Okay? So anybody who picked a color that is different than its neighbors, right? For instance, this node, right? It's kind of successful in the sense that that's the color that it will keep permanently. Okay? Let's say we keep those colors, and those that were not successful, they're going to kind of back off from this choice, right? And try to pick a color again, right? The only thing that is good to do, and it helps in kind of making the algorithm faster, is that, but let's update the kind of the palette from which these nodes are choosing, right? What do I mean by updating them? You know, if a color is taken permanently by one of the neighbors, let's remove that color because I don't want to create a conflict with those neighbors again. Okay? So this is what's known as Johansson's algorithm from 90s. The point being that he, I guess, kind of gave a simple analysis of it. So for instance, here again, they picked a random color. So these two nodes kind of got unlucky, but the rest are good. They keep their colors. Those nodes try again. This time they got lucky, and so on. So that's the end of the coloring. Okay. So simple algorithm. Let's try to think about the analysis of this. The very first round is very simple to analyze. You know, for each node, I'm picking a color from a palette of size delta, right? The probability that I pick something that is different than the neighbors is roughly like 1 minus 1 over delta to the delta, right? Constant. The next rounds, one has to be a bit more careful in the sense that it kind of depends on the palette remaining for you and for the neighbors. They're not exactly symmetric, but one can make a one-liner argument, convexity, and so on, and see that per round, each node has a constant probability of success. Okay? And therefore, you know, within order of log n rounds, everybody is colored with high probability, with probability 1 minus 1 over poly of n. Okay? And this means there's a log n time randomized algorithm for the problem. So any question about this algorithm? So, all right, so coloring is one of the really old problems, has been studied for a long time. I'm going to, since I kind of talked about the problem, I'm going to mention the state of the art for it. The current state of the art is roughly log squared of log n. Okay, and perhaps more important to mention is that it comes from this kind of a complexity, which is one term is log star of the maximum degree. Okay, and this solves nearly the entirety of the problem. It kind of colors almost every node in the graph with the exception of some small components here and there disconnected from each other. Okay, so this is known as the shattering, kind of graph shattering thing. It comes from the study of lowest local lemma and actually came to distributed computing by way of local computation algorithms. And then kind of there are these components that are of size poly log n. We kind of know that inherently you have to solve these things with a deterministic algorithm, and the best known is roughly log squared of log n. And throughout the talk, I'm going to mention a number of problems that remain open. This is one of the easiest ones to kind of to note is that, you know, can we get something that is, you know, let's say smaller than log n? It's even plausible that there's a log star algorithm for this problem. We don't know anything better, or we don't know how to. And the other thing that I want to mention is that there's this concept of almost clique decomposition. There are a number of variants of it. This was originally introduced by Bruce Reed in the study of relations of, you know, chromatic number, clique number, and max degree. And this was used, for instance, in these works of Harris, Schneider, Su, and Chang, Li, Petty. It kind of decomposes the graph into sparse regions and dense regions with really nice properties. Please come to Seper's talk. He will tell us much more about this and all the amazing things that are possible by using this and other nice ideas. Good. So let's talk about a different problem. One of the, you know, old graph problems, max matching, or approximations of maximum matching. And it will be convenient to think about this as an LP, okay, even though it's kind of an overkill, but let's think about it as an LP, right? You know, I want a matching. I am allowing to have fractional values for each edge, right, between 0 and 1. The usual constraints of matching, meaning that for each vertex, the summation of these fractional values of the edges should be at most 1. And the dual of its minimum vertex cover, right? So for each edge, you want that the fractional values of the vertices sum up to at least 1. Okay? So here's a classic algorithm for solving, basically both of these matching and vertex cover algorithms. It's kind of an instance of primal dual, okay, with a bit more care about how to change the parameters at the same time to get a good round complexity. Okay, we're going to start with a trivial fractional solution for matching, 1 over delta, right? So this is clearly feasible in the sense that if I add these values for each vertex, it's at most 1. Right? Good. So let's do the following. So we're going to have roughly log delta round. If you're looking at the slide, perhaps you can think about epsilon as a small constant or even just 1. So for each vertex, let's add the values of the fractional, the fractional values of the edges incident on it, right? If these values are adding up to something close to 1, right? Basically, that constraint is almost tight, right? So I don't really need to increase more there. I can kind of freeze the values of those edges, okay? I don't need to increase them anymore, okay? So let's do the following. For each vertex, if the summation of these fractional values around it is more than, let's say, 1 over 1 plus epsilon, I'm going to freeze all the edges of that vertex, okay? And then after that, for each of the edges that remains unfrozen, I'm going to increase its value by some multiplicative factor, let's say by a 1 plus epsilon, or you can think about by a 2 factor, right? Epsilon being 1. And this is kind of implicit in a work of Kuhn, Maske-Broda, and Wattenhofer, although the idea was kind of, I mean, they do something much nicer for a more general category of problems. So let's see this. A simple animation will help us. Let's say this is the graph, and these are the initial fractional values, right? So let's say 1 over 8, 8 being the maximum degree here. So clearly, this is a feasible starting point. These vertices, if you look at the summation of the values around them, they're roughly above half. So I'm going to think about epsilon as 1. Okay. So I will freeze the edges incident on those vertices, right? And then for every edge that remains unfrozen, so bold edges are now frozen. These edges that are not frozen, we will think about increasing them by a 1 plus epsilon factor. And epsilon is 1 in this animation. So let's say I increase them by a 2 factor. Right? So we do that. Now the values are a bit higher. Then these vertices get frozen, right? And so those vertices get kind of tight, and then the edges get frozen, and then we go to the next round and next round. Okay. So is the process clear? Is the algorithm itself clear? So it's a very simple algorithm in roughly log delta of these rounds. Basically makes every edge frozen, right? Because for every edge, you start with a value of 1 over delta. Until it's frozen, it's growing by a 2 factor, let's say, right? So within log delta rounds, this edge is going to be reaching a value of, let's say, 1, right? So it will be frozen unless one of its endpoints was already tight before and the edge was frozen before that. Okay. So, and this gives, let's say, roughly a 2 approximation. Here's a very simple argument. I'll do the argument only for opt being an integral matching, but you can also generalize, of course, easily to a fractional matching. So let's say I have this opt, right? Let's do a local argument because locality seems to be useful here. Let's say I start with kind of $1 on each of these edges. Okay? On each of the edges of opt, okay? What I'm going to do is kind of pass this $1 to the endpoint of the edge that is tight. Okay? So we know that by the end of the process, for each of the edges, at least one of the 2 endpoints is tight, right? So I'm going to pass this $1 to this endpoint that is tight, okay? And then I'll ask that endpoint to kind of spread this money to the edges proportional to the fractional values that they have, right? So of course, the summation of these fractional values is large. It's larger than 1 over 1 plus epsilon, right? So each of these edges is going to get a value roughly at most the fractional value of it times 1 plus epsilon. Now, each edge receives that much money from one of its endpoints. It might receive that much money from both of its endpoints, right? But kind of overall, what we are seeing is that, I started with opt dollars, right? In the end, each edge has at most 2 plus epsilon times its fractional value, which means the summation of the fractional values cannot be too small. It's at least opt divided by 2 times 1 plus epsilon. So does that make sense? Is it? And you can see a very similar argument, or even kind of without this argument, that if I output these vertices that became tight, that's also a good vertex cover. It's like a 2 plus epsilon approximation of vertex cover. Since I talked about this, and I was talking mostly about fractional matching, I'll mention here that if we are in the world of randomized algorithms, it's easy to round the fractional matching if I'm willing to lose, let's say, a constant factor, right? In just constant rounds, you can do randomized rounding and get something a constant factor smaller, and then you can repeat this idea constant times, get close to a 2 plus epsilon approximation. If you're talking about deterministic algorithms, we don't really know how to do the rounding quickly. The best that we know is roughly log squared of delta by a work of Fisher from 2017. And this is the second open problem that I want to mention, just because it's super easy to state, right? So you're given a fractional matching. We want to compute an integral matching within a constant factor of the size. How quickly can we do that? Good. So that's the end of what I wanted to mention about distributed algorithms. Hopefully by now the model is clear, right? It's just about how many of these rounds of communication do we need to to do a computation for each of the nodes of the graph. Any questions? Yes.
Are there any lower bounds for those local probes?
Okay, so there are a number of lower bounds actually. Okay, so it's not showing up on the slide, but I should have mentioned maybe. Okay, it's not here. So there are lower bounds not for the rounding, but for the matching approximation. Okay, so maybe I'll mention it here. I'll write it here. So there is roughly a lower bound of root of log delta divided by log delta. That's a lower bound on any constant approximation of matching, and this is a lower bound by Kuhn, Moshe-Broda, and Mohsen. And as a function of, I'm sorry, like this is not a square root. As a function of n, the best lower bound that we know is roughly log of n, square root of log of n. So this holds for any constant approximation of matching. And actually, I'm going to refer to this lower bound later on in the talk. This lower bound holds also for randomized, so it doesn't make a distinction. Maybe about that, if you're talking about deterministic algorithms, and we insist on maximal matching, right? Locally, it should be kind of really a CSP like with local properties. Then there's a lower bound of roughly log n for deterministic algorithms. But for randomized, log n is the best lower bound.
Excuse me. In the same vein, is an approximation better than 2 really hard? Is that no?
No, it's not hard actually. I mean, there's an easy way of going from 2 approximation to 1 plus epsilon approximation.
Oh.
So that doesn't make a kind of huge difference. And like old stuff, like Andrew, I guess McGregor had this kind of general result. I guess I don't see kind of that's with a kind of a loss of a 2 to the 1 over epsilon, you can go from, let's say, any constant to 1 plus epsilon, right? Nowadays, there's even a transformation with a poly of 1 over epsilon.
Okay, I understand.
So yeah, 1 plus epsilon is not so much harder. Yes.
Any lower bounds for the previous problem? Because you said maybe you can get log star. Or...
No lower bound for that, with the exception of log star of n itself.
Okay,
in the original work of Nati-lineal, there was a log star of n lower bound, and that's the best that we know. Still. Other questions? So let's see this connection to things called local computation algorithms. And this is a model that was introduced by Ronit and colleagues. I guess we'll see a bit more about the story of the model. So the idea is that it's an attempt at kind of making a model for sublinear algorithms. Okay, so let's say I have a giant graph, and I want to design a sublinear algorithm for this graph. Okay, so what do I mean? Here's one way of defining a sublinear algorithm. Let's say I want to have access to each single part of the output. Okay. And for me, the task is to kind of figure this single part of the output in time that is sublinear in the size of the entire graph. Okay. So for instance, I want to know, in a given, like in a computed coloring of this graph, what's the color of this given node? Or in a computed vertex cover, small vertex cover of this graph, is this node in the vertex cover or not? In a maximal independence set, is this node in the maximal independence set or not? Okay. So, let's be a bit more specific about what's the access to the graph. So let's say this algorithm, which I'm going to call an LCA, a local computation algorithm, it has query access to the graph. Okay, so it can pick a vertex and say, give me the fifth neighbor of this vertex. So let's say it gives me the ith neighbor of the vertex. So that's the only access that this algorithm has to the giant graph. And what we want to do using this algorithm is give access to any single part of the output. Let's say there's a claim, this algorithm is kind of claiming that it has computed the maximal independence set of the graph. Okay. Now we go and ask it, okay, is this vertex in the maximal independence set? And it will answer yes or no. Okay. We will ask another vertex, it will answer yes or no. Okay. By the way, I mean, the algorithm I guess, has not computed this maximal independence set, right? Because that would take time to actually read the entire graph, right? It's kind of creating the illusion that it has computed the maximal independence set already, right? By way of answering these queries. Okay. There's a critical property that we need from this LCA, that the answers that it's giving to our questions should not be depending on kind of the questions that we have made to this algorithm. Okay? They should not depend on the previous questions that we have asked from this algorithm of whether this vertex is in there or not. Right? Without this property, the problem is kind of trivial, in the sense that the LCA can just remember the vertices that it has said yes for it, right? And every time that I ask, it just looks whether one of its neighbors has already been declared to be in the independent set or not, right? And if not, it puts this new one in the independent set, right? So it would be very trivial. But it's super crucial for all the ways that people use these LCA algorithms, that the answer should be independent of the queries made to the LCA. Okay? And as a matter of fact, these LCAs should have a small memory, which is another reason that you cannot remember the independent set, but we don't even need that property in defining the model. Okay. So what's the main measure of interest when talking about LCAs? The question is, to answer a single one of these questions about whether this given vertex is in the independent set or not, the LCA is going to make a number of queries to the graph, right? And the main parameter or the main measure of interest is how many of these queries will it make to the graph. Right? And of course, also the memory that it will use and the time complexity that it will use, they typically happen to be kind of related to the query complexity and usually within a polynomial of it, so I will not talk much more about that. A crucial property that is needed in most of the applications is that we really care about the worst case number of queries made to the graph. Okay? Meaning that, if you think about any single vertex, how many queries do I need to make to the graph to answer? This worst case bound is much more important and needed in many of the applications rather than, let's say, expectation or average or things of this kind. All right, so why is the model defined this way and why is it useful? Okay, there are a couple of examples. One very standard one is that, if I have a giant graph and I want to estimate some kind of parameters of this graph, right? Let's say you want to estimate roughly the size of the maximum matching in this graph, right? One natural approach is that I'm going to pick, let's say, random vertices in this graph, right? Let's say this random vertex, right? And if I have a local computation algorithm that, if I ask it, answers whether this node is matched or not in some fixed maximum matching, right? Then by sampling a few of these vertices and seeing what fraction of them is matched, I get an estimator of the size of the maximum matching in the overall graph, right? One has to be a bit careful about, the additive error here, depending on whether the graph has a lot of isolated vertices or not, and the multiplicative error. I'm not going to open those. The base idea is that, you know, by having this local access to a matching algorithm, right, I get an estimator for the size of the matching in the overall graph. So that's one of the base ideas in how LCAs show up. Right? Question or yes?
Yeah, typically, do you have a bound on the number of queries you might have to support?
No. So the number of queries can be arbitrary, and you know, typically it doesn't reach n in the applications because we are interested in sublinear algorithms, but there's no bound.
Is there a connection to the previous model?
That's the point of this talk, so we're going to see that. Good, good. Okay, so here's a second example, which I find, well, let's say, less trivial and also more exciting. So there was this beautiful work by Arsen, Jane, and Ronit, which kind of makes use of these LCAs to get something in learning. So in particular, you know, there was this thing in Eric's talk yesterday about learning for monotone functions on the hypercube, right? So there are these old results that give a learning algorithm, but they were improper in the sense that the output function is not necessarily monotone, right? So it's learning for monotone functions. Okay, so this is the work of Bishuti and Tomon, or I'm probably pronouncing the name wrong. Okay, so the really nice thing that they did is that, you know, they kind of take this improper learning algorithm, which is not guaranteed to be monotone, and they kind of do local corrections to the output function, okay, and turn the function to be a monotone function. Okay? So it's a local corrector for the algorithm, so therefore they get a proper learning algorithm. And the core, okay, if I'm simplifying a bit, the core is that, you know, you need local access to a graph, right? And you will kind of try to find the matching of this graph, a maximal matching of this graph. And that maximal matching, the edges of this maximal matching will be places where kind of there's a violation of monotonicity, okay? And you're going to basically correct that in the sense that you're going to swap the values along this edge, okay? So that will give you a bit of correction here, right? And by way of using this on the graph, sometimes on kind of a power of the graph, longer distances, they fix the non-monotonicities, right? So I will not talk more about this. I think it's a very nice example of how LCAs can be useful in settings that, at least on the surface, it's not clear why they're connected to LCAs. One thing that I want to mention about this example is the parameters, because actually the parameters, I think, are instructive. So the graph that they have is kind of this hypercube, right? Like, let's say it's a capital N-dimensional hypercube, right? The number of vertices here is, you know, at least the part that they really care about. You know, you can drop basically epsilon fraction of the hypercube. The number of vertices is roughly exponential in the dimension, okay? The maximum degree, it ends up being roughly, you know, if I'm thinking about the bulk of this graph, like if I drop the epsilon fraction away, the maximum degree is roughly 2 to the square root of a capital N. Okay. So, and the algorithm that they end up needing for solving, let's say, a maximal matching is roughly polynomial in this degree. Okay. So this is the interesting thing. And actually, if you think about the graph as a size of the graph, this is roughly 2 to the square root of log of n. That they need. Okay, so it's a complexity that is, you know, it's a strange complexity that you really need to solve, right? So, you know, like linear time algorithm or even square root of n time algorithm or so would not imply anything of interest here. So it really has to be polynomial in degree, and the degree has this 2 to the square root of log n behavior as a function of the size of the graph. All right. Question? Yeah.
For LCS, for maximal matching, is it possible even to hope to get polynomial again LCA for maximal matching? Or do you need dependence on the
I think you have to be a bit more careful about the model then. What does the model give as an access to the graph? Do I get a single edge? Do I get the entire neighborhood?
No, I think a single edge.
A single edge. Okay. I don't know a formal lower bound, but my suspicion is that the delta would be a lower bound.
The Parnas run lower bound applies that. Give you omega delta lower bound. Yeah.
All right, so Parnas run is the name.
Sorry, wait, Parnas run will require log n, though, like it's not.
No. I think it's delta. It's actually root n in the instance that they set up, and it's actually. Thanks for. Good. So okay, so now is there a connection to the previous thing that we were talking about? Right? There is one very simple connection. You know, whatever problem that you pick on a graph, if you know that this problem has a distributed algorithm with round complexity R, then this almost directly, or actually completely directly, implies an LCA for this problem, where the query complexity of this LCA will be delta to the R, maximum degree to the R. Why? Well, you know, to know the output of this vertex, I'm just going to gather the R-hop neighborhood of it, right? Simulate the distributed algorithm on it, and give the output, right? So that's delta to the R. And Parnas run actually, before the definition of LCAs, used this connection to give a sublinear time algorithm for approximating vertex cover. Okay, since we have seen the algorithm for vertex cover and max matching, you know, let's look into it a bit closer, right? You know, we saw this algorithm that is roughly running in log delta time, right? You just put it directly into the simulation argument, right? You get a LCA for 2 plus epsilon approximation of vertex cover, which has complexity delta to the log delta, right? So quasi-polynomial in the max degree. By the way, I don't know why in that paper somehow it was written as a log delta approximation for vertex cover. I think something is overlooked. It's a simple 2 plus epsilon approximation. Good. So is that connection also clear? It's a very, very direct connection. Good.
What if your algorithm is randomized?
But if your algorithm is randomized, you know, at least on the surface, if you somehow think about the randomness belonging to each node, you can do the same thing, right? Often, if you want to do something proper, you have to analyze. Okay, so what do I mean by, like, what do we mean by consistency?
That you want the local views would give me a global.
Right, okay. So, you know, if I think about a consistent way of generating the randomness of each single node, then I get that consistency directly, right? If I have a way of, you know, for each node as a function of its number, ID, right? So there's a question of, you know, how do we do this kind of with a small source of randomness, right? Often we end up having to analyze these distributed algorithms, right? And observe that they actually have simple properties, simple sources of randomness are sufficient for them, and then we generate those PRGs.
Or maybe just focusing generically because you just need it to be like delta.
Right. Another way is to use generic and say that these are small space computations, and then therefore, I mean, it doesn't end up being super efficient this generic way, but yeah, that's another completely generic way of using this source of randomness. All right. So, well, so this is delta to the log delta roughly, right? At least for this problem, right? What more would we want? Right? Okay. Of course, one thing is that we want better dependency on delta, right? So polynomial in delta was, for instance, one thing that was asked, right, before. Second one is that in some of these applications, it's not so much about the approximation factor, but more about satisfying some local properties. In particular, maximality ends up being useful, for instance, in the learning setup, right? Maximality has this property that, you know, locally you have a fixed guarantee, like you have this guarantee, you know, like either this edge is in the matching or one of the incident edges is in the matching, right? It's not the case that there are some small parts of the graph where you're giving no guarantee, right? So in some applications, maximality is really needed, right? So that's the second thing that kind of is desired. And actually, you know, kind of goes back, like the kind of the answers to these questions goes back to couple of other papers that are also before the introduction of the LCA as a model. So there's this well-known result of, you know, Shishtav and Goyen, which kind of basically gives an LCA for an MIS, for a maximal independent set in the graph. Okay, the way that this thing works is that, you know, of course, MIS is a problem that we can solve using greedy. You know, I can just go through the vertices and put them in a greedy fashion in the MIS or not, right? Let's say I pick a kind of random ordering of the vertices and go through this order, and try to put the vertices in a greedy fashion in the MIS, right? So they give a very nice kind of argument that to figure out the answers to this greedy MIS, I don't need to run the entire greedy, and by way of some local accesses, I can generate this result. The result that they had was that in expected 2 to the maximum degree queries, I can figure out each single part of the output, right? And there was this elegant kind of, let's say, improvement by Yoshida, Yamamoto, and Ito, which cuts the query complexity to be basically linear in the maximum degree. Okay, it's also expected linear in the maximum degree. There is one subtlety that this one is not about the expected query complexity for every node, but for, I mean, it's actually a bound on the average of the query complexities of different nodes. Therefore, in some sense, it's kind of, it's a bound on the expected query complexity for a random vertex. Okay, and let me stop there about that one. So these things don't really give a good bound on the worst case query complexity, right? In the sense that if I think about expectation of the maximum of the query complexities of the vertices in the graph, right? At least a naive thing would have an n factor roughly to union bound over all the vertices in the graph, right? So that's not really a great sublinear time access to the graph, right? And there have been attempts at kind of trying to get this stronger property about all the vertices of the graph. So for instance, there was this work of, Ronit and colleagues. They get basically a maximal independence set, but not for the entire graph, but let's say for a 1 minus epsilon fraction of the vertices of the graph, right? And the query complexity for these will be roughly poly of delta divided by epsilon times some polylog. And they use this to give, for instance, constant approximation of matching, 1 plus epsilon approximation of matching by kind of fixing augmenting paths, kind of flipping augmenting paths. And these are roughly poly of delta for any constant epsilon. Okay. There was this nice work recently that kind of does a different thing and gets the complexity to be even linear in delta times log n. Okay. So not even poly of delta, but linear in delta times log n. There was the work of Sohail, which kind of gets a different way of talking about these things. There's a distinction whether kind of these are queries to the edges or to the vertices, right? I'm going to summarize it and say that it gives roughly a 2 approximation of the size of the matching, right? Let's say with an additive epsilon n error, and the round complexity or the query complexity will be roughly linear in the maximum degree times some polylogs and divided by epsilon squared. So that's one line, the approximation world, how things have improved, right? This other side is really getting maximality, which is the thing that is needed in some of the applications. The original paper gave a complexity of delta to the delta times log delta times some polylog n. Okay. And the question in the area was kind of getting poly of delta log n, right? For instance, in the learning application, this was what's needed. Right? There's been a sequence of improvements getting to quasi-polynomial, right? And then even eventually to polynomial in delta, okay? And I think the last thing that really gets poly of delta is an extremely messy algorithm. I can say that because it would be really nice to get a, let's say, a linear in delta algorithm, potentially even quadratic, but a nice algorithm. And the reason that I'm bringing that one up is that it actually really comes through this connection from distributed algorithms. Okay, so there's this distributed algorithm for the problem that roughly runs in log of delta time. It shatters the graph, and remaining parts are small and can be handled easily. Okay, so itself directly gives a complexity of delta to the log delta, right? So it will be quasi-polynomial in delta, right? But then there are these ideas that, for this algorithm, I can massage the algorithm, I can do things to it in the nature of sparsification. Because of that, I don't need to gather the entire ball that is relevant, the entire log delta hop neighborhood, right? I can do kind of smarter simulations of the algorithm, right? And gather only polynomial data size about this neighborhood. And that gives poly of delta.
Or something.
So it has to do pruning things. It ends up working a bit. Yes, in some sense it is pruning. Okay, It actually works much more kind of in the distributed side, in the sense that it kind of tries to build a distributed algorithm where per round each of these nodes only looks at constant many of its neighbors. Okay, like, I mean, it doesn't really get that. But if it was only constant many neighbors, then constant to the log delta would directly be poly of delta. It's a little bit like that. So this is kind of, why is it possible that I only look at constant many neighbors is in some sense pruning. I mean, in the papers it's called sparsification, but that's just terminology. It's all about pruning. Yes?
What was the lie?
Great. Okay, so what's the lie? So this one says that the components are going to be small, and it says they're going to be of size polylog n. They're not really of size polylog n. They're of size poly of delta times log n. For some purposes, one can kind of reduce the problem to polylog n size instances. For this LCA world, actually poly of delta log n is also perfectly fine size in the sense that, you know, this chunk of poly of delta times log n is small enough that I can just read the entire thing and give the answer. Good. So we have seen now, you know, this connection from distributed algorithms to local computation algorithms. I want to now go to this third world or third model, which is about massively parallel algorithms. And, you know, at least the origins or the motivations of this model come from, you know, this whole mindset that data is growing extremely fast, you know, in some sense faster than the capacities of single computers. You know, this might be their memory, or it might be their capacity to process data in a fast way, right? And at least on the practical sides, there has been a lot of work, you know, popular frameworks that use the power of many computers to solve problems faster, right? You know, you probably have heard things about MapReduce, Hadoop, etc., right? This whole area, it's an emerging field in theoretical computer science, tries to kind of contribute to this area by way of, you know, theoretical foundations, right? And the model was originally called MapReduce. Nowadays, it has upgraded to massively parallel computation. It's a simple concept. It says, you know, let's think about some problem on a data of capital N bits, and N is perceived to be a very large value, right? And let's say this data is partitioned among the computers, okay, in some balanced way, let's say even randomly, okay? So each of these machines has a smaller capacity. Let's say it has a memory of S, which is much smaller than N. So you can think about this as polynomially smaller than capital N, maybe root of N, or I don't know, N to the 0.9 or things of this kind. And generally, capacity actually can be kind of modeling a few different aspects. It might be memory, it might be communication capacity per time unit, let's say, or some computational limitations. It's an abstraction of many of these things at the same time. Memory is maybe the cleanest thing to think about. Okay, so the computation again in this setting goes in rounds. In each of these rounds, each of the machines gets some S bits of data, can do computations to this S bits of data, right? And then it can pass the information to other computers, right? So the only limiting factor here is, you know, the S bits of data given to each of these. One can ask the computation inside these rounds to be nice. I'll come back to that later. And the base question is, how many of these rounds do we need to solve the given problem? Right? So in some sense, this is a kind of a coarse-grained way of viewing parallelism. Okay, you know, the classic way of viewing parallelism, let's say PRAM and so on, was this extremely fine-grained view that, you know, you think about many processors, they do a single RAM operation, right? That's kind of one step of computation, right? They should happen at the same time. You go to the next single RAM operation. Maybe they pick two numbers, like one of them picks two numbers, adds it up, right? So these are really kind of fine-grained view of, like, these are simple operations that they have to do in each of these steps, right? So this MPC world is kind of a much more coarse-grained view, which says that, you know, if you give me a small enough chunk of data, right, if it's like, let's say, a root of N, or I don't know, N to the 0.1, I can dump it to one of the computers, ask it to do some computation, hopefully a nice computation, and that's just one step of parallelism, right? And I just want to parallelize these steps across these different computations, right? And because of this is actually kind of related to the bulk synchronous processing framework that Valiant had. In some sense, this is a simplification of BSP. BSP has many parameters and kind of it's very general. It's hard to work with it from an algorithmic viewpoint. It's kind of a simplification of BSP, and it captures.
Are we allowed some redundancy? Like, can we store the same peak in multiple?
To some extent, we are allowed some redundancy, and actually, let me look into it by talking about graph problems. Okay, so when we are talking about graph problems, we think that the graph is partitioned among these machines, right? In some balanced way. Okay, perfectly fine if there is some redundancy and each edge is maybe kept by some number of these processors. It's not a necessity that there's no redundancy. Okay. These processors can talk to each other directly, meaning that, if I have a single bit of information and I want to pass it to somebody else, I can just directly send them this message. So something about this redundancy. Okay, so I'm thinking about each of these computers having a capacity of, let's say, S, right? And if I denote the number of computers or machines that I have by capital M, and we're going to be talking about graph problems, right, mostly. So clearly, M, the capital M, has to be large enough that the entire graph fits into these machines, right? So it has to be at least number of edges divided by the capacity of each of them. Usually, we assume that it's not much larger. Okay, let's say within polylogs of it. Although this is not it's not a main source of difficulty in the computation. Often, many of these things that we try to solve, at least from our theoretical understanding, even if I increase this by a polynomial, it's not clear how to make the problem much faster. Okay, so it's not really the main limiting factor. But of course, if you want a nice algorithm, this should be small. Right? And for instance, this perfectly allows us to have redundancy. We can kind of create many copies of each of these, let's say, edges of the graph. Matter of terminology, this capital S, sometimes we call it local memory. It's the memory of each of these single computers. And the total memory in the system, which is the number of machines times S, we call that global memory. Okay, so good. So our focus is on graph problems. We have understood that kind of the complexity of graph problems changes in some way drastically kind of as a result of how S compares with the number of vertices of the graph. Okay. So, kind of one regime of interest, at least early on, was when S is strongly superlinear in the number of vertices of the graph. Okay, so let's say n to the 1 plus some constant. Okay, so this was one regime that was studied a lot. Okay. Another regime is when the memory is roughly linear, let's say n times polylog n or n divided by polylog n, right? And the third regime, which in some sense is the hardest of them, is when the memory is, let's say, n to some constant. Let's say the memory of each machine is, let's say, n to the 0.99 or n to the 0.9. Okay? But critically, it being sublinear in the number of nodes, in the sense that it's not even possible for a single computer to know all the vertices of my graph. Okay? And this last regime is sometimes called fully scalable. Kind of these are the most desirable of the algorithms. If you have an algorithm for this setting, it also applies or implies algorithms for all the other settings. You can kind of easily simulate this smaller ones. Okay. So what do we know about, let's say, graph problems, right? So we have been talking about matching, right? That was our example, at least in the first part of the talk and a bit in the second part. So for matching in this superlinear regime, there is a constant round algorithm. Okay? And we will talk about it in a minute. Okay? The best that we know in the near linear memory regime is roughly log of n rounds. Okay? And in this last regime, the best that we know is roughly square root of log n. Okay? In the fully scalable world, it's roughly square root of log n. Questions? All right, so we talked about coloring in the first part of the talk. I'll mention the kind of the state-of-the-art complexities. I'm not going to go over it. So let's focus on one of these and try to understand, what are the basic algorithms that one can do in these models, right? So I'm going to focus on this constant round algorithm for matching in the strongly superlinear memory regime, right? So here's the statement. So let's say each of my computers has memory that is n to 1 plus some constant, small constant. I want to build an algorithm that solves the, let's say, maximal matching problem in roughly constant, in kind of 1 over delta, delta being a constant, so this is a constant round complexity. So that's the purpose, or that's the thing that we will talk about. Here's a very simple idea. Suppose that, I'm currently thinking about this graph and it has m edges. Right? Let's mark each of the edges of the graph with a probability that will basically make sure that the sampled edges or the marked edges, the number of them is small enough that I can push them into one machine. Okay? So let's say, for instance, I'll set the probability to be, n to the 1 plus delta divided by m. Right? So this is going to mark roughly n to the 1 plus delta of these edges, right? With high probability no more than that, right? I'll take those edges, put them in one machine. Now that these are in this machine, I'll ask that machine to pick, let's say, a maximal matching of those edges. Okay, greedy matching of these edges. And then I'll clean up my problem in the sense that, for any vertex that already has an edge in this matching, right? I'm kind of done with that vertex. I'll announce that this vertex is matched, right? And I'll kind of remove this vertex and all of its incident edges from the problem. So simple algorithm. This is a single iteration of this algorithm. So I want to say that just a few iterations of this finishes the job. And let's focus on one iteration. My claim is that after one iteration, the number of edges of the graph will go down by roughly n to the delta factor. So if I repeat this roughly 2 over delta or so, I'll be done. Okay? And the proof is extremely simple. Let's think about any potential set of vertices that might remain. Okay, let's denote that I. Okay, so this is any potential set of vertices that might remain. Okay, the question is, the graph induced on these remaining vertices, can that be dense? Can it have a large number of edges? Right. The point is that if this induced graph had roughly kind of a bit more than m over n to the delta, right? Let's say 10 times more. In some sense, we would expect at least one of these edges to be sampled, right? And then you can do an simple argument that, with a probability 1 minus exponential in n, one of those edges would be sampled, right? Even if a single one of those edges is sampled, that means that, this vertex set I cannot be a set of vertices remaining, because at least one of the two endpoints of that sampled edge would have been matched, right? And this concentration is good enough that I can union bound over all possible choices of set I, right? Over all the 2 to the n choices, which means with high probability there's no such set of vertices that induce a dense subgraph, right? Therefore, every iteration reduces the number of edges by n to the delta factor. In 1 over delta of these iterations, we would be done. So a very simple algorithm does the job in constant rounds. Any questions?
It doesn't seem that you really use the MPC.
Great, yeah, this algorithm doesn't really use. I think it's a very nice instance of seeing that for some problems, especially if you're well above n, right, it can kind of be broken into a small number of very easy instances of MPC, right? And there are actually interesting results that essentially we only need one of the computers or one of these machines to be of memory n to the 1 plus delta, right? The rest of them are doing much simpler things and they don't really need that much capacity. We just need this single center to have a bit more capacity. This is known as a filtering technique. It applies to a number of other problems. Yes?
Are there separations that are known between those three regimes?
Between the regimes. Good. So, in some sense, you're asking, like, are there lower bounds, right? The truth is that there's no lower bound. There's no proper lower bound. Here's a joke explanation of them. It's nowadays known that MPC is as powerful as transformers, meaning that the number of rounds of MPC is equivalent to the number of layers of self-attention. Right? Or like for any MPC algorithm, one can build a transformer, and for any transformer, one can build an MPC with a constant number loss in both directions, right? And of course, we all know transformers are super powerful. There cannot be a lower bound against transformers. That's the reason that we don't have a lower bound. Okay. On a more serious note, here's a reason that kind of we don't have a proper lower bound. So there's a fairly simple argument that, even for this n to the constant memory regime, if there was a lower bound that is super constant, okay, and if this is an unconditional lower bound, this would separate P, the class of polynomial kind of time problems, right, from NC1, kind of the circuits of depths log n with polynomial size, right? And this would be a major result in circuit complexity. Like we have almost no idea how to approach these things, right? What?
That's more convincing.
Yes, thank you. Good. I'm going to come to some of these assumptions. We don't know. I mean, for some limited family of algorithms, we know things and so on. Okay, so now what's the reason? The reason is actually fairly simple. If you give me a circuit and it's of depths, let's say log n, right? It's fairly easy to simulate this circuit using an MPC algorithm. And that kind of the number of rounds will be roughly log of n base s, base kind of this local memory. Okay, so if s is n to some constant, this will be just constant number of rounds. And the reason is fairly simple. If you give me this circuit, right, basically I'm going to put one computer or so responsible for simulating each of the gates of this circuit, right? And it can kind of look at kind of log s height of that circuit, right? Gather the relevant data, simulate that part of the circuit, right? So I kind of can go a log s factor deep into the circuit in each of these single rounds. That's why kind of MPC can easily simulate circuits, and that's kind of part of the difficulty that we have with giving any unconditional load. Now, well, can we say something limited? Can we say something conditional? For the regimes of memory that are, let's say, linear in the number of vertices of the graph and above it, I'm not aware of any really generic conditional lower bound. That's somewhat unfortunate because we really could have could benefit from some explanations of why our algorithms are stuck. For the memory regime where the memory of each of these computers is sublinear, let's say n to the 0.9 or so, there's a good bit more explanation. Okay, so for instance, there's this seemingly super simple problem. Just distinguish whether the graph is a cycle with n nodes or it's two cycles with n half nodes, right? I mean, this should be a trivial problem, right? We don't know how to do this, and there's a conjecture that this should take at least log n rounds. This is a conjecture that nowadays we are using this as a basis to explain some of the other round complexities that are stuck. This way of looking at it might give the illusion that just because these objects are large and they're larger than the memory of one computer, one cannot put kind of these objects into the local memory, and that's the difficulty. I think that's kind of a wrong way of viewing it. Here's a different way of stating the lower bound, which I think is a bit more informative. Even if I think about graphs where components are fairly small, okay, let's say each of them is a path of length d, okay, and you pick two vertices s and t, you ask me, are these things connected to each other or not? This seems to require log of delta rounds, okay, it's kind of implied by the previous thing that log of delta is a lower bound on this, right? And notice that these are, I can even set delta to be much smaller than the memory of each of these machines, so it's not the problem of putting one of these structures in the memory. It's just a question of, how can I gather all the relevant data into one machine? I originally start with some arbitrary partition, let's say only a random partition, right? And each of these computers that is holding, for instance, this node, right, has to get the information of this path. The best that we know, it kind of goes exponentially. In I rounds, I get to know roughly 2 to the I neighborhood of a node, right? And that's where things are stuck, okay? Yes?
So you said omega log d follows from the previous one when d is n, but now you're applying it to d equal root n.
No, I did not say that it's, okay. If I said that it follows from the previous thing when d is equal to n, I misspoke. I mean that there's a way of getting this one from the other one by way of simulations and arguments and so on. So one can get this as a hardness. Okay? For d, let's say for d that are not too large and not too small. seen. Okay, and okay, so log of these seems to be kind of the right way of looking at this problem. And as a matter of fact, we know that this is roughly the right bound from the algorithmic side, but there have been a number of really nice results that get roughly log of d as the upper bound on the connectivity problem, plus roughly a log n, and nowadays even deterministic and fairly simple algorithms. Okay, so log of d is roughly the right way of thinking about connectivity. Now, okay, we talked about. Okay, so we haven't really arrived at algorithmics and connection to distributed. Maybe I'll talk about lower bounds first and distributed computation. Okay, so can we get some conditional difficulty, right? Some explanations of why things are stuck. Here is one limited way that we can give some explanations. It kind of says that MPC algorithms that are fully scalable, meaning that they are in this, let's say, n to the constant memory regime, right? They cannot be too much faster than distributed algorithms. Okay, they can be exponentially faster, but not much more. Okay, that's kind of the explanations that we have. Right? There are some technicalities. Kind of the only thing that we know is that this applies to algorithms that are component stable, meaning that algorithms where the output for one component, for one connected component, doesn't depend on other connected components, right? At least on the surface, this seems to be an intuitive thing in the sense that, if I'm computing a matching inside the component, right, why should it depend on the other components? But it's not trivial to lift this kind of this issue, and we'll see much more about this. So for instance, I mentioned that for constant approximation of matching from the distributed side, we know some hardness, like square root of log n. We know that any algorithm that computes constant approximate matching has to have a leakage of information from distance that is further away, more than root of log n away. Okay? So, one can really kind of use this, right, or put this into the problem, right, and get a conclusion that, okay, any MPC algorithm for this problem that is fully scalable needs at least log n rounds. At least if we assume this 1 versus 2 cycle conjecture, this omega of log n hardness of distinguishing a single cycle from 2 cycles. Okay? And on the very high level, kind of the informal intuition here is that, if there is an MPC algorithm that runs much faster than, let's say, log n, okay, it's kind of getting some information from far away, from outside the relevant neighborhood, really quickly, right? It's getting it in less than log n time. So it has a kind of a leakage of information from far away, okay? And you can kind of use this leakage to actually solve connectivity faster, okay? So one can show that, if there is such an algorithm and it runs in little of log delta time, kind of getting some bit of information from outside the neighborhood, right? This might be a very kind of hard to extract bit of information in some sense, right? But some bit of information from outside is coming in less than log delta time. We can leverage that and solve connectivity in little of log delta time, which runs into a contradiction with the conjecture, right? So that's a partial explanation of which assumption? The log delta? Okay, so the assumption is only used at the last step that log delta should be the hardness of connectivity. So we are running into a contradiction with log delta being a lower bound on connectivity. Right? I mean, it gives a proper algorithm for connectivity. You can use it to solve connectivity faster than log delta if there was such an MPC algorithm that is faster. It runs into a contradiction with the 1 versus 2 cycle because it's giving a connectivity algorithm that is too fast to be true. All right. Please come to Arthur's talk. He will tell us much more about lower bounds in this setting, right? And also, hopefully, he will say much more about this seemingly technicality of component stability and all the nuances that go into it in defining it properly and why we are stuck in removing that assumption. Good. So we have seen, yes.
Can't you always assume without loss of generality for matching programs connected? So now the vertex connected to everyone doesn't change the matching.
Depends on what problem for matching. Okay, like, are we saying that algorithmically adding edges to the problem to make it connected?
Yes.
Okay. So And like to which nodes do we add edges?
No, I'm saying that when I want to design an algorithm for matching, I can just assume without lots of generality my graph is connected.
So why is it without lots of
I pick the
generality?
vertex, I'm connected to everyone.
Okay, so yeah, I mean, up to a size of 1, I can make it connected, right? So good. So now, I mean, now this is saying that now the entire connected component is getting impacted if I make a small change here, right? So now this is kind of killing component stability, right?
In the original.
Right. I mean, now kind of there is, now there are dependencies in this graph. I mean, there should not really be a dependency for the matching size because, you know, the most that this can influence is a +1, -1 in the matching size, right? But at least on the surface, now there's only a single connected component and everything is dependent on each other.
The lower bound.
Now we don't, in some sense, we don't have an explanation of why the algorithms are stuck anymore. Right. So we talked about, you know, this constant round algorithm. I want to quickly say something about this result in the fully scalable regime. Okay, and maybe I'll mention something about the middle one. Okay, so we want to have an algorithm that roughly in square root of log n rounds solves the problem in the memory regime that is, let's say, polynomial in n, let's say n to the 0.9 or so. Right? The reason that I want to talk about this one is that it's really, really connected to this whole log delta algorithm that we've been talking about from the beginning. Okay? So, you know, there was this log delta round algorithm, right, from the distributed side, right? I kind of want to simulate this algorithm, right? But I want to simulate it a good bit faster than log delta rounds, okay, using the power of MPC. Here's what we can do. You know, let's take these log delta rounds of the algorithm. Okay. Let's break them into, let's say, kind of a groups of root log delta rounds, okay, phases of root log delta rounds. Okay. So now my task is going to be essentially simulate each of these phases in something close to a constant, let's say in log delta rounds. So if I can simulate each of these in log delta rounds of MPC, overall I get a complexity that is roughly root log delta. Now, so let's focus on just a single one of these, the very first phase, right, of this process in the gray box, just for the first root log delta of the rounds. Okay. Now, if you stare at this process just for the first root log delta of the rounds, right, these fractional values, right, they start with 1/delta. They don't change too radically within the first root log delta rounds. They only change by, you know, the maximum that we can have will be 2 to the root log delta divided by delta, right? So they're not changing too radically. And the decisions that we are making about these variables is some kind of linear thresholding decisions, right? So these are easy things to simulate by way of sampling, okay? So we can essentially sample the edges of the graph with some probability that is not too large, okay, let's say 2 to the root log delta divided by delta, and on the sampled graph, we can simulate the original process, okay. So now this moves us to a graph where the maximum degree is only 2 to the root log delta, right, at least for this part of the problem. Now this is a graph of degree 2 to the root log delta. I want to simulate a root log delta round process, right? So the entire neighborhood that is relevant for me is 2 to the root log delta to the power of root log delta, right? And you can set the constants properly so that this entire neighborhood is small enough that it can be put into one machine. Okay? For each part of the graph, the relevant neighborhood is small enough that can be put into a machine, right? There's still this issue that, you know, okay, it can be put in the sense that it fits, but do I get it actually quickly, right? That's actually not a hard thing. There are simple ideas, you know. If the graph is generally sparse enough that the local neighborhoods can fit into the machine, I can do the following, you know. Basically, in one round, I can go from the graph to G squared. You know, I can make every node learn, you know, basically it's 2-hop neighborhood. But when I repeatedly apply this in I iterations of this, every node learns it's 2 to the I-hop neighborhood, right? So kind of a log of the relevant neighborhood radius is all that it takes to gather this data into the node itself, right? So, you know, if I have a T-hop algorithm, it takes log of T rounds, right? And what we did previously was basically sparsifying the graph so that these local neighborhoods are small enough to fit into memory, right? And that roughly gives us a complexity of root log delta. I want to make a note. It might be a technical one, but I think it's a good observation. One should keep this in mind. The complexity, at least the way that we described it, is actually log of the maximum degree divided by root of log n. You know, the radius that we can simulate is root of log n. And the reason that I'm making a note of this is that actually for lower bound graphs, for these things that are hard, this actually ends up vanishing, and actually kind of the algorithm gets a complexity of log log n. So actually for the hard instances, the upper and lower bounds are matching in some sense, at least for these instances. So you know, one really has to come up with different graphs to give an explanation above log log n. Good. And you know, common ingredients that show up in this connection between fully scalable graph algorithms and distributed algorithms is that, you know, okay, so one simple thing of this graph exponentiation, right? This is an old idea, basically pointer jumping from PRAM literature. Right? So that's something that commonly shows up. The other thing is sparsifying distributed algorithms, a little bit connected to this pruning thing, right? I mean, trying to kind of build a different distributed algorithm that doesn't need the entire neighborhood, right? And can work with a much sparser part of the neighborhood. So variant notions of sparsification and proper definition of approximation for these things shows up in many of these algorithms. Good, so we have now seen these two things, right? And this will be the topic of Slobodan's talk. Please come to that talk, which is immediately after this, right? So he will tell us much more about this log log n. I've been mentioning open problems. I'll say some of them here. You know, basically beating these two bounds, both of them remain open. Little o of log log n in the first case, little o of square root of log n basically in the second case. One of them that is a bit more seemingly technical, but I really like it because I think it gives us a simple explanation of where things are stuck, is basically do the thing that Slobodan will tell us for hypergraphs of rank 3, where each edge has 3 endpoints. Okay, so please listen to his talk and see where things are getting stuck if I have a hypergraph of rank 3. So that's good. So I used to talk about, you know, kind of, there's a vast literature, there are kind of ways of accessing a survey of this lecture notes. There's now recently also a book on the area, right? So I think it's a great source to read on at least some of the basic results in the area. So hopefully now you have some idea of what I mean by, you know, locality showing up in these seemingly different models of computation, and the fact that it ends up connecting these different areas to each other, and how techniques from these fields have found ways into each other. I'll stop here with a list of open problems. Thanks a lot for your attention.
We already had some questions, but if there's any more, any questions about the model, about the results?
Yes. So in MPC, does it matter how you partition the graph into different machines?
Technically, yes, in the sense that if it's a nice partition, some problems are easy. Right? I mean, for connectivity, if each part is given, then connectivity is trivial. Right? Usually, the assumption is that it's a balanced partition, but we make no other assumption about it. Or at least our algorithm should not really make an assumption about it. Right? And often, we even think about just a random partition as a good way to start. It seems to be practically the relevant way. Yes, so please.
Going back to the first question about component stability, if we are given the assumption that the input is just connected, can we, like, is it true that like matching requires log log n rounds just based on one cycle to cycle?
Technically, we don't know.
Oh, we don't know.
But I think we are cooking into the problem and unnatural. I mean, we're trying to find an explanation of why our algorithms are stuck, right? We don't have a formal lower bound. This connectivity, I don't know. One might say it's a red herring, but we don't really know it as a formal result. I mean, connectivity should not really be impacting the size of matching.
More questions? Some. Okay. Yes.
Actually, I have a question for LCS in particular. You mostly mentioned graph problems. I know that SOIC was introduced. Do you know of any LCA that deals with other type of problems?
Maybe let's do it. Do you want to answer that?
Okay. I have a
We
lot.
have only limited time for coffee break, not half an hour.
Maybe I'll take that offline. But the answer is yes. There are LCAs for other problems.
Any final question? The last chance. Okay, the last thing Mohsen again, and let's just meet 5 parts.